We're doing a deep dive today into the science of things you probably handle every day without even a second thought. We're taking a common, really recognizable kitchen herb. I mean, it's the bedrock of so much savory cooking. And we're going to treat it like a complex biological machine.
And the herb is common sage, or Salvia officinalis.
Right.
And if you have a bundle of it sitting in your kitchen, you should really grab it, hold it up to the light.
Yeah, do it.
You'll see it has this incredible, almost
dusty texture and a silvery gray sheen.
Exactly. And that's our whole mission today, to uncover the fascinating science behind that specific look.
Yeah.
Because what just looks like simple texture is actually a complex, ancient survival strategy. It's perfectly engineered.
It really is.
Okay, let's unpack this.
So when you look closely at that sage leaf, you are literally looking at millennia of evolution.
Wow.
This plant is native to the Mediterranean. So you have to think intense, dry heat, long droughts, scorching sun.
A really tough place to live.
A very tough place. And every single physical detail we're about to talk about is a direct response to those pressures.
So the survival plan is basically baked right into the plant's body.
Exactly.
And this is the part I love because we have some really specific, memorable terms for these features. So you can sound like a botanist by the end of this.
We do. There are two key anatomical features that really define the whole look and function of the sage leaf. I can start with the sort of the
Structural component.
Go for it. What is it?
The first is the surface itself, the topography, which we call rugose.
Rugose.
Yeah, rugose. It's the term for that signature, deeply wrinkled or
corrugated texture of the leaves.
So if you compare it to something smooth, like a basil leaf.
Exactly. Basil is flat. Sage has these hills and valleys and deep folds.
It's not a flat plane at all. It's like a little topographical map, all rough and rugged.
That's a great way to think about it.
Okay, so that's one. And what about that famous silvery fuzz that covers everything?
That is the second feature. And it's maybe the most critical one for survival. We call them trichomes.
Trichomes.
These are those dense, soft, silvery layers of hairs that cover the entire leaf surface. It's what gives it that grayish, almost felt-like texture.
So you have the rugose hills and valleys, and then they're covered in this dense forest of fine, soft hairs, the trichomes.
You got it.
It feels tough when you touch it, almost like armor, which I guess makes sense if it evolved in such a harsh climate.
It is absolutely armor, but it's multi-purpose armor.
Oh.
The trichomes aren't just one type of hair either. They're complex. Some are just mechanical. They stand there for protection.
Okay.
But others are what we call glandular
Trichomes. And these are the specialized little factories responsible for making and storing all those volatile essential oils we want.
Wow, I had never considered that. So these little hairs are both physical protection and they're chemical storage units.
Yes.
That immediately sets the stage for the rest of this. So we established the what. Now we have to get to the how. How do these structures specifically fight off the two biggest threats in the Mediterranean? And drought and just extreme heat.
That is the core challenge, absolutely.
Yeah.
And it brings us to this ingenious biological system for basically water management.
Okay, so mechanism one, preventing catastrophic water loss.
Right.
In a dry, hot place, plants are constantly losing moisture through their pores. It's a process we call transpiration.
Right. Plant sweat, basically.
Plant sweat. So how does the combo of
The rugose surface and the trichomes physically slow that process down.
They work together to create what scientists call a boundary layer.
A boundary layer.
Yeah, just imagine
A still, humid layer of air right above your skin. That's what the plant is trying to create for itself.
Okay.
The dense covering of those trichomes, it traps air and it stops it from moving right next to the leaf's surface.
Oh, so it's like putting on a thick fleece jacket.
That's a perfect analogy.
The fleece itself isn't warm, but it traps the little pockets of air your body warms up, and that creates insulation.
That is exactly what's happening. The air trapped by the trichomes becomes saturated with water vapor that the plant releases. And because that little layer of air is now super humid, the difference in humidity between the leaf surface and the dry outside air is, well, it's much smaller.
And when that difference, that gradient is smaller, the rate of evaporation or transpiration, it must slow down dramatically.
Dramatically. The leaf is effectively humidifying its own microclimate.
Wow.
And the rugose texture helps in this whole process.
It increases the surface area, but it also creates all those little pockets and valleys where the air movement is restricted even more.
So it's a dual action design.
It is. It ensures maximum water retention
In a place where every single drop counts. Unchecked, transpiration would just dry that plant out in a few hours of intense sun.
Okay, That explains drought survival. But what about the sun itself, that intense scorching sunlight? We know the silvery color is really distinctive, but is that just a side effect of the or is that a specific adaptation too?
That is mechanism 2, temperature regulation. And this is where the silvery color of the trichomes is so important.
Okay.
It's a direct strategic adaptation. The technical term is high albedo.
Albedo, that refers to reflectivity, right?
Yes, just think about surfaces. Dark, smooth surfaces, like a shiny green spinach leaf.
Yeah.
They absorb nearly all the solar radiation and they heat up fast. The sage leaf, covered in this dense layer of silvery white hairs, is doing the exact opposite.
It's maximizing reflection.
Maximizing it.
So the plant is basically wearing a highly effective, reflective thermal blanket.
You could say that. The trichomes are acting like a huge
Field of microscopic mirrors.
Wow.
They're bouncing a significant chunk of that incoming solar radiation away from the actual photosynthetic tissue. And this reflection keeps the leaf temperature cooler, even when the air around it is scorching hot.
So the same structure that traps moisture is also reflecting heat away?
Yes.
So it's preventing water loss and preventing the plant from overheating and shutting down all at once.
Precisely. It's an incredible case of form-following function.
Every single detail has a purpose for survival.
It does. It also lets the plant keep its stomata, those are the tiny pores for gas exchange, open for longer during the day without risking lethal water loss.
Because the cooling system reduces the heat stress.
Exactly, the heat stress that would normally force those pores to clamp shut.
That clarity is so helpful. It helps you understand that the texture isn't just some quirky feature. It's a fully integrated
Life support system.
It is.
But we are only halfway there, because those exact same physical structures, the rugose surface and especially the glandular trichomes, they're not just passive barriers.
They're also the infrastructure for the plant's active chemical defenses.
And here's where it gets really interesting.
Okay.
Because now we shift from physical protection against the environment, sun, and drought to chemical protection against other organisms.
Pests and pathogens.
Exactly. The plant needed to build a storage facility, and it decided to integrate it right into the existing water management system.
So the place where the plant holds its water is also the storage unit for all the potent stuff we actually love in the kitchen.
That's it.
So tell us more about the essential oils themselves. What exactly are they?
They're highly complex mixtures of volatile organic compounds. In sage, this means things like thujone, camphor, and cineol.
And those are the compounds that give sage its signature earthy, pine-like, sometimes a little peppery or pungent.
That's the flavor profile, yeah.
We experience that aroma and flavor as a culinary delight. But, you know, if we put on our evolutionary biologist hats...
The plant didn't make those for us.
Right. It didn't evolve these volatile compounds just so...
Our Thanksgiving stuffing would taste better.
Not at all. And that brings us to the second, and for the plant, the most vital function. Natural defense.
Okay.
These highly aromatic, often pungent compounds, they act as a really powerful chemical deterrent.
How potent are we talking? Is it just a mild smell that says go away, or is it more like a specialized chemical warfare system?
Oh, it's much closer to the latter. Yeah. Compounds like thujone, which is so characteristic of sage, are actually neurotoxins to many insects.
Whoa.
So if a beetle or a caterpillar decides to take a bite, the oil released from those glandular trichomes, it tastes terrible. And in many cases, it actively harms the pest. It makes the sage leaf a very unattractive meal.
So it's a risk-reward calculation for the insect. The reward of water and nutrients is just not worth the risk of consuming toxic thujone.
Precisely. And it goes beyond just
Chewing insects. The essential oils are also critical for fighting biological threats that need moisture.
Like what?
Well, many fungi and bacteria, they thrive in humid conditions, which is,
it's a bit ironic.
Wait, why is it ironic?
Because the sage leaf is working so hard to create that microhumid layer right near the surface to hold on to water.
Oh, I see. So the same system that solves the drought problem trapping humidity,
Right.
it could potentially create a brand new problem, a breeding ground for fungi.
It raises that risk, yes. Which is exactly why the essential oils are so vital. They have strong antimicrobial and antifungal properties.
Oh, okay.
By stocking the trichomes with these chemical compounds, the plant makes sure that the localized humid microclimate it created for hydration is also chemically sterilized against any opportunistic pathogens.
That is a beautifully synthesized defense mechanism. Just incredible.
It is.
So the physical features, the rugose surface, and the trichomes, they protect
The plant from the environment by managing water and temperature.
Correct.
And those very same structures serve as the warehouse for the chemical compounds that protect the plant from
other organisms like pests and fungi.
The whole system is integrated for maximum resilience. It's a masterclass in efficiency.
It really is.
The plant adapted one structural system, this dense layer of hairs, to solve three totally distinct problems: reducing transpiration, reflecting sunlight, and housing its chemical defense arsenal.
It really makes you look at that humble herb, crumbled on the kitchen cabinet with a whole new level of respect. It's not just an ingredient, it's a veteran survivor. It's covered head to toe in biological engineering.
And every chef who relies on that powerful flavor is, well, they're essentially using a plant's ancient, highly refined defense chemicals.
Yeah, so what does this all mean? Let's recap the main takeaways for you, our listener.
Okay.
By looking really closely at a single leaf of common sage, you can read an entire biological history. Its specific anatomy serves three core interconnected functions, all vital for Mediterranean
survival. First, massive water retention, thanks to that rugose structure and the insulating trichomes.
Right.
Second, temperature regulation through the silvery high albedo reflection
of those same trichomes. And third, essential oil storage inside the glandular trichomes for both the flavor we love and for a potent chemical defense against biological threats.
The big lesson here is that the plant's form is a direct response to, really, existential pressure.
Right.
And this leads us to our final thought, which connects this amazing biology back to the simple challenge of gardening.
Yes, the source notes highlighted how much trouble people often have growing sage, even though it's so hardy in the wild.
It seems counterintuitive.
It does. If this plant is so perfectly adapted to harsh, dry, intense, sunny, and, stressful environments, what happens when we try to cuddle it?
That's the provocation, isn't it? So many gardeners, they kill sage with kindness.
How so?
Rich soil, too much water, plenty of shade. This fundamentally contradicts the plant's entire blueprint. This plant
Evolved under nutrient-poor conditions, where it had to deploy its defenses constantly.
So the argument is that the intensity of the flavor, the concentration of those essential oils, the thujone and the camphor,
is a direct reflection of the environmental stress it's under.
That's the idea.
A pampered plant in moist, rich soil might grow big and green.
But it won't need its full chemical arsenal.
I see.
Exactly. It doesn't need to fight off fungi if it's not in that overwatered soil. And it doesn't need to produce high concentrations of neurotoxins if there are no hungry pests around. Its potency, which is what we want for cooking, it diminishes.
So the key to successful cultivation, if you want to maximize its flavor and its resilience, is not to pamper it.
No. It's to mimic those harsh Mediterranean conditions that forged its defenses in the first place.
You have to let it fight a little to make it truly worthwhile.
You do.
It really encourages you to think about how closely plant care has to mimic the native, challenging environment to actually achieve the plant's maximum function and flavor.
A fantastic challenge.
It's a fascinating challenge to take away from such a
humble, fuzzy leaf.